In this lesson, we'll examine visual imagery, working memory, and the reactivation hypothesis. So both fMRI and lesion data suggest that the brain has a few places that seem dedicated, specialized for processing certain kinds of stimuli. Here we see three of them. We see the body area, we see the fusiform face area here, mostly on the right, a smaller patch on the left. Remember, this is reverse, so we're looking at the bottom of the brain here. So this is the right fusiform face area. And then the parahippocampal place area. So faces, places, and bodies seem to have special regions on the cortex that are processing those stimuli. So early on, Kanwisher and her colleagues wondered what happens to these areas when a subject is simply imagining a face or a place. Will these areas also be activated just as they are during perception of a face or a place? And sure enough, her fMRI data suggests that imagery activates the corresponding places in the brain. Now here we see in the top here is the fMRI data for the fusiform face area, and the bottom for the parahippocampal place area. And what she's going to instruct subjects to do is during the perception phase of the experiment, they're simply going to be watching a computer screen when a face comes on, and then they'll watch as a place comes on, in this case a little house icon, face, house. So during perception, they're simply passively watching the screen. But then for another block of trials, they're going to have different instructions. They're going to ask the subject to imagine a face or a place, a face or a place, and then do another block of perception trials, and then imagery, etc. And you can see pretty clearly here that during the perception phase, when they're looking at a picture of the face, sure enough, the fusiform face area shows significant activity, and the place area not. And that switches, it reverses when the picture of the house comes on. So when the place picture comes on, fusiform activity declines and parahippocampal place area significantly increases. And you get this nice alternating signal, faces, places, faces, places. But you find the same kind of alternating signal in the imagery condition. Now, granted, for a face, imagining a face produces a little bit less activity than actually seeing a face on the screen. But nevertheless, it's the same region of the brain that is involved in imagining a face that is also used for seeing a face. And likewise for the place. So even during the imagery condition, you get this alternating signal. Increased fusiform face area for the face, and then it gets quiet for the place, but the parahippocampal area shows increased activity for the place, and then things reverse for the face and the place, etc. Now, the idea of generating a mental image, so eyes are closed, but we can still sort of call up an image in our mind's eye, so to speak, is an example of one of the contents of working memory. Now, working memory, some folks like to call it working storage, but working memory is an important system in the brain. It operates over a few seconds, so it's different from long-term memory. Of course, we can store memories for a lifetime, but the working memory system is a system that makes information available over short periods of time. So we can think of it as a temporary storage system for whatever information is being activated and that we're currently thinking about. The system allows us to manipulate information. Maybe we're doing some mental math. We're adding numbers in our head. Maybe we're imagining a map and figuring out how to get from place A to place B. So whenever we have to sort of think about stuff, we could be just thinking about somebody's argument and whether their conclusion follows from their premises. When we're manipulating information, we're using the working memory system. Of course, it's also intimately related to the attention systems in the brain. So whatever's in working memory, the idea is we want to limit distractions. We want to be able to focus our attention on whatever information it is that we're manipulating. So if we call up an image, then the imagery would be the current contents of our working memory system. Now on a brain, we're going to represent this working memory system as a box in the frontal lobe here. Now it is true that that when scientists use fMRI to study the working memory system, there are regions of the frontal cortex that are reliably activated whenever a person has to hold information in working memory. But there are also parietal regions that are consistently activated. But we're just going to show the frontal lobe portion of the working memory system. And the idea in this picture is that if we're asked to call up an image, what can happen is the frontal lobe system here can reactivate a portion of the visual system. And that reactivation is what allows the imagery then to come into our mental experience. And so we would indicate that by putting visual imagery here in the box. So whatever's in the box will be the content of our working memory. So when somebody's asked to imagine a face, for example, the idea is that cue will be entertained in working memory. The person understands the instruction, and that cue will be used to reactivate visual memory systems, and then that reactivation generates what we call a visual image. Of course, we could also have other things in our mind, right? Verbal thoughts. If we think about it, we often go through the day and we have thoughts in our head. They're usually sort of in some kind of linguistic form. Well, the idea is similar here, that those thoughts that we have in our head are the activation of language areas in the brain. They're being activated in such a way that they produce the verbal contents of our thoughts, right? But again, we would conceptualize these verbal thoughts as being the content of our working memory system. And we'll learn later exactly how this system may be related to other areas of the brain. For now, the idea is that the working memory system can sort of interact with other parts of the brain, activating different parts of the brain to provide the contents of working memory. In this case, either verbal thoughts or visual imagery. So let's now contrast imagery and perception again using the face example. Here we see the right hemisphere and the eye here, and here's Joe out here, right? So when we look at Joe's face, visual information is going to be traveling back to the visual cortex. That's the early stage of visual processing in the brain. And then we have our fusiform face area down here, right? So it gets its inputs from the earlier stages of visual processing. And so when we look at different people and we learn about different people, we can store memories of faces. And so we want to think about the idea that perceiving faces can alter our brains in such a way that we can store a representation of the different faces that we see. So face perception, we're going to call this perception, right? Because the visual system is being activated by the world. So face perception results in stored representations of different faces, and we can think of these as sort of like face memories. But while perceiving a face, of course, we're activating the visual system externally. What's going on when we imagine a face? Well, here the idea is that the cue to imagine Joe's face is going to be a signal that reactivates Joe's stored face representation in the face area and perhaps other areas as well. And when that face memory is reactivated, that then provides the contents of our visual imagery. Notice we're putting it in our working memory box here. So the cue is going to be used, so the instruction to imagine Joe's face is going to translate in terms of brain activity a signal back to the place in the brain where face memories are stored. A particular memory, Joe's face, will be reactivated and we will experience Joe's face as an image. Now notice then, the fact that face perception regions, right, the fusiform face area, are active for imagery suggests that face memories are partially stored in those same regions used for face perception. Right, and now we're going to call this the reactivation hypothesis. So imagery is an example of internally activating memories. In contrast, perception, of course, there's something in the world, an actual face in the world is going to activate the visual system. Imagery is an example of internal reactivation of memories. And we're going to call it reactivation here because we already kind of have to know what Joe looks like if we're going to activate an image of Joe. So we can sort of define loosely our reactivation hypothesis here. We'll say those regions used to process stimuli are also used to store memories that involve those stimuli. So when we see faces, when we perceive faces, the fusiform face area is activated, but when we imagine faces, the fusiform face area is reactivated. It's just that we're doing that activation internally as opposed to externally. And the same would be true for places. We can imagine places. It's just that the reactivation signal is not going to turn on the fusiform face area, but it will turn on the parahippocampal place area. Now, lesion data also supports the reactivation hypothesis. Let's take prosopagnosia. This is the face blindness. So again, here we have the right fusiform face area here. Damage to this area is correlated to perception deficits, right? Face perception deficits. And we've seen examples of people with prosopagnosia. But here's the interesting thing. Not only do they have difficulty perceiving faces, but they have difficulty imagining faces, right? And that's exactly what you would expect if the same bits of tissue that are used for perceiving faces are also used to reactivate for the purposes of internal imagery, right? So patients with prosopagnosia have difficulty perceiving faces but also imagining faces, and that supports the reactivation hypothesis. There are even some interesting cases of painters, for example, who are well familiar with colors of paints and so on. They've been painting all their lives. They get focalized brain damage in part of the cortex that processes color. Well, now they no longer see color. But of course, they've been living all their life with color perceptions, but now they don't perceive color anymore. And interestingly, neither can they imagine color. So again, supporting the reactivation hypothesis. And the same is true of the patients with damage to the parahippocampal place area. They have difficulty finding their way around in places along a city block, for example. So they have difficulty sort of perceiving and navigating where they are, and they also have difficulty in the realm of imagining places in their mind. One final piece of evidence that supports the reactivation hypothesis goes way back to the early experiments by Roger Penfield and his stimulation studies. So he was a surgeon, and when he was doing surgery, he would often stimulate the cerebral cortex of patients while they were awake to map out the cortex. And what he would find is that the stimulation of some of these regions in the temporal lobe here, the superior temporal lobe, not all the time this would happen, but if the patient reported a memory, it tended to be an auditory memory, whereas stimulation of more posterior temporal and occipital regions, here the memory tended to be a visual memory. And that again supports the idea that the places of the brain that are used to process visual information are also being utilized to store memories of the visual aspects of events, and the same with auditory.